Hi, you guys. Happy Tuesday. We're going to talk about the periodic table today, and the name of this unit will be periodicity. So, periodicity really just refers to the quality of being periodic, which is just the tendency to reoccur at intervals. So, it implies that there are some patterns, and it implies that things are occurring over and over again. And the periodic table is very much an example of this. So here's a cool image that I like because it gives us the context of where we would commonly see a lot of the elements. And it gives us an ability to start to sort of get a feel for some of those themes and patterns in the table. You can see most of the table is metals. Some of our really, really large elements, we don't actually know what they look like because they exist so briefly that they just fall apart before we can even study them. And so a lot of those are named after famous chemists, and so that's why you see pictures of some people on the table as well. Over here we've got some of the things that occur more naturally as gases, and in particular you can see the noble gases, and they are often what we use in neon signs. Obviously we use neon in neon signs, but we use some of the other guys as well. So just a little bit of a history of chemistry and how we got to the periodic table. Before we had chemistry, we had alchemy, and alchemy was sort of employing principles of chemistry, but in a less scientific way. And alchemy had two goals. You were looking either for what they called the philosopher's stone, which is kind of like this elixir for life, or you were looking for gold. So you're either trying to turn normal stuff into gold, or you were trying to find a magical, excuse me, yawning, some type of magical elixir for immortality. And somewhat ironically, everybody always put mercury in those because mercury is really cool, right? It's a liquid metal. It looks cool as hell. So then it was like, here's the elixir of life. It has an incredibly poisonous heavy metal in it. So, oh, now you're dead. Guess that didn't work. But anyway, they were trying to figure some stuff out. And this painting, I think, does a good job of kind of capturing for us, you know, the feeling of that balance between the scientific and the sort of mystical nature of alchemy. You can see this alchemist, and he's just discovered phosphorus in its pure form. And phosphorus, of course, is where we get the word phosphorescent, which is just to say that it glows. It glows on its own. It creates its own energy and radiation that it puts off. And it's not necessarily like radiation like we think of with like radioactive uranium, but it is a type of light, a type of radiation. And so this originally was painted by Joseph Wright of Derby in 1771, and then he kind of finished it up and touched it up a little in 1785. But he named it The Alchemist, comma, in search of the philosopher's stone, comma, discovers phosphorus, comma, and prays for the successful conclusion of his operation, comma, as was the custom of the ancient chemical astrologers. But now we pretty much all just call it The Alchemist Discovering Phosphorus because that title was hella obnoxious, and also contained like crazy capitalization. So I recreated that here, and I don't really know what that's about, but you know, it's all good. So in that time period, by 1700, only 13 elements had been identified. We didn't know a lot about a lot of the elements because they're always like bonded and stuck to other stuff. And so at that time we were trying to figure out like what's the most pure form of, you know, matter, and we had figured there's like 13 different kinds that seem like they can't be broken down any farther, but that was only 13. From 1765 to 1775, they discovered 5 elements. So, if you think about like the history of humanity, and, we found 13 in all those years. And then in a 10-year period, we found 5 new ones. And we were like, whoa, God, 18, that's a lot. So I want you to take a second, think about what was happening during that time period of 1760 to about 1820-ish that may have helped account for the sudden increase in these discoveries. Ultimately, in that time, the Industrial Revolution was happening, and it kind of started in England and it spread throughout the world. And that allowed for some significant scientific and engineering advances. And that's why we saw this big jump in the elements at that time. So now that we have 18, people started to really think like, we should try to organize these, maybe kind of look for some patterns and understand how they behave. So people started to work on that in the mid-1800s. Mendeleev is a Russian dude. Well, he's not alive anymore. And as you can see from his photo, he truly has the look of a crazy Russian scientist, which I highly approve of. And he was incredible. In 1869, he published a periodic table of the elements. And what he did is he organized it based on repeating properties. So he put them into the groups based on how they behaved. What do they react with? And that kind of thing. Then he also organized it by increasing atomic mass. So he put on note cards, actually, he would put all the information that we knew about an element on a note card, and then he would arrange those note cards into different groups until, some patterns started to jump out at him. And when he did that, he eventually came up with a version of the table we use today. So something I get asked sometimes is like, why didn't Mendeleev use the atomic number to organize this table? And I want you guys to think about that for a second, because like it was 1869, right? So basically, he just didn't, they didn't know atomic number, right? Like they hadn't discovered the subatomic particles. They were just starting to understand maybe there's some positive parts and negative parts of the atom or something. And so he didn't know like, oh, this one has 3 protons, So he was just using the mass to kind of estimate, which mostly worked. Excuse me, y'all. It put a couple things in a wonky order, but like mostly it worked okay. So here's a picture of his table. You can see some of the groups and families that we currently know on our own periodic table. So here's a little hydrogen. We don't have helium because helium is an inert gas, meaning it doesn't really do chemical reactions. Like it's super useful for, balloons and MRI machines, but it was hard for us to actually discover helium. So we have hydrogen. Hydrogen's super reactive, so that was easy for us to find. Lithium, also super reactive, easy to find, but yeah, helium is like, we didn't know it existed. So we've got hydrogen, no helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. And so that first column on this table is our first row on our modern periodic table. You can also see, if we look from left to right, lithium, sodium, potassium, rubidium, cesium, right? All those guys are in the first column of our periodic table. And so there are some really amazing similarities. You can kind of start to see how we based our periodic table off of Mendeleev's periodic table. So my favorite feature in this table, y'all, is the question marks. So you can notice right in the middle here, it's like copper, zinc, question mark, it should weigh about 68, question mark, it should weigh around 70, arsenic, selenium. So Mendeleev was very confident in his table and in the patterns he had observed. So he was like, listen up, y'all, there are some missing elements. I don't think they said y'all in Russia, but maybe there's like a Russian word for y'all. That'd be cool. So down here in this lower left corner also, you can see there's more where he's like, do these really go here? Maybe, maybe not. But yeah, he started to make these predictions, like this element, 180, it's got to exist because there's a hole, and that to me is pretty incredible. To notice patterns and have so much faith in your own chain of logical thinking that you're like, no, my table's not wrong. There's an element we haven't discovered. Like, all right, my dude, that's pretty righteous that you're just like owning it and just saying like, my plan is perfect. Like, there's things missing. Y'all need to discover those elements. So the other thing that was kind of cool in that time period is that some other people were coming up with a really similar organizational scheme at the same time, and they were noticing the same patterns. So like one of those dudes was Julius Lothar Mayer. He published a really similar table around the same time. And the reason Mendeleev gets all the credit is that his was really like the first one, because he delayed publishing it because it wasn't done. He's like, can you please discover this element so I can publish my table? And then he also was just kind of working on perfecting his theory around it. But he was like, he just published it in like a textbook that he used because he was like a professor. So he wrote a textbook and he published it that way. And then everybody was like, wait, hold up. Like, what's this thing? And so it's just an interesting situation when you have a bunch of chemists that aren't necessarily communicating with each other, studying similar things, and then it turns out they're all kind of coming to the same conclusions independently, and that can be a powerful indicator that there's some good thinking going on there. Okay, some other people made different designs of the periodic table. There's lots of different ones. My favorite way to do it is actually to cut it out and like make it into a cylinder. And there's a little video y'all will watch that kind of he talks about that. But here's some others that are just my favorites because they're just ridiculous. So Ingo Waldemar Dagobert Hach proposed this table, which is, a thing of beauty. And starts with hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, and it has this cool swirl situation happening. You can see some of the families are still lined up here. So noble gases, helium, neon, argon, everything that makes up that far last P6 column of the periodic table. And we've got some of our other families. Here's like lithium, sodium, potassium, rubidium, cesium. So it's not perfect, but it's still, it's just fun. It's a spiral. And then we have this one, which they just go in order. Hydrogen, we didn't know about helium yet. Lithium, beryllium, boron, carbon, nitrogen, oxygen. And this is really for sort of different purposes than our periodic table. It was looking at patterns of, is it monatomic? Is it diatomic? So does it usually bond with one atom? Does it bond usually with two atoms? Does it usually bond with three atoms? And then if it's paramagnetic or diamagnetic, which has to do with electrons and stuff like that, which definitely in this class we don't really care to get that in depth, but I just thought it was like a very interesting organizational scheme as well with the zigzag and the dashed lines, and I'm like, all right, Crooks, do it up, buddy. Like, this to him for what he was trying to do was probably really, really helpful for the way he was organizing the elements at the time. Notice that I assumed that Crooks is a he. I don't know the first name, but given the time period, there's pretty much a 95% chance it was a dude. Or it could have been a lady, but then her husband published it, even though it was her idea. That used to happen a lot also. Because you couldn't just be a lady chemist. You had to like be a lady chemist and then, pretend through your husband that you were a real person. Summer. Here's our real periodic table. You'll notice that if we really wanted to have it be representative of electron configurations and everything, we would put the lanthanides and actinides in here in the middle in this long part. But then it doesn't fit on a piece of paper as good, so that's why we kind of changed it up.